Good morning, good afternoon, good evening. I'd like to first welcome you and announce that that before we begin, I want to inform you that any mention of specific products and services in this webinar is not it does not represent an AWWA endorsement. AWWA does not endorse any products or services. And with that, we begin our session on machine intelligent non-acoustic leak detection. My name is Chuck Hansen. I'm the chairman and CEO of Electroscan, and we're going to go to our very first quick poll question. And in it, it's very simply, what is your non-revenue water, NRW, in percent? So A, 0. Our agency has no NRW. So there are some out there that do. B, 20 to 30%. C, I'm sorry, B was 10 to 20%, C was 20 to 30%, D 30 to 40%, and E is more than 40%. I'll let you put your answer. No wagering, there's no right question in this. And then we'll get instant results from AWWA. Okay. We've got some that are perfect, 21%. Look at that. And there are some that are over 40%. So great, great information there. What I'd like to do now is introduce you to our speakers today. It's a great gathering. I'm just delighted. My background, I've been in the business for about 40 years. If you've heard of Hansen software, done a work order, done an inspection, done a hydrant test in Hansen, that's me. And I'm also delighted to have Charles Wilmot in Dallas. Charles and I actually go back almost 30 years, Charles, from that City of Houston project in 1990, where we televised 5,000 feet of that project there. So delighted to have Charles. And also from jolly old England, where it's just a few minutes past 6 p.m., Brad Weston. Brad is our managing director at Electroscan UK. He's going to talk about a number of very interesting projects from the UK. And notice 3,000 insertions on both tethered and untethered acoustic. So Brad, it's great to have you. Our agenda is going to be pretty straightforward. We'll go through an introduction, just some industry information. Charles will join me and we'll talk about, in a conversation, the technology. Then Brad and I are going to talk about case studies, and then we'll open it up for questions. So with that, we'll just get going. So 40 years, 1980, I just turned 65, so been at this a long time. And when I came back after selling Hansen, I got the question, do we really need another way to find a leak? We've got some, I would say, outstanding technologies that have hunted and identified a number of leaks, for the last 100 years. But they all pretty much had one thing in common. And if we looked at the past and present of acoustic and some of the data loggers, there's no secret that we don't use these technologies to actually approve new installations. I mean, we're pretty much using hydrostatic testing. So this notion of leak detection and water tightness testing is a big gap in trying to improve our leak detection capabilities. We've had a lot of success with acoustic data correlators, finding that leak location between 2 points above ground. We can do that very quickly. The problem that we've been hearing over and over and over again is, yeah, we did a clamp on that. We're now going back to that very same pipe. And it's not just once or twice, but 3, 4, 5 times until we do that. Why can't we just identify that pipe profile correctly the first time? And really what we're asking, is there a way to determine, do I have a single a crack, problem, joint, leak? Do I have something at every joint? Is the problem random throughout the pipe wall, at the service connection, at the tap, at a joint? Or is it concentrated? Because when I go through my AI to actually come up with repair rehabilitation strategies, that's the information that I'm really looking for. we all know the challenges. The acoustic vendors, some of which may be on this call, don't like to hear this, but the environmentals are really against us in a lot of cases. We know, for example, that just use of a household, there's a good reason that we're using acoustic listening sticks and correlators and data loggers at night when there's not a lot of use. We do know, contrary to popular belief, that if I've got a leak and it's filling around the pipe, that is an instant insulator to that leak. And I'm relying on that exit wound or that exit point of the pipe really to give me that vibration as we go forward. Pipe size and material. We're not going to go into it, but a lot has been written. A lot of folks really have seen what can be found in plastic pipes. We all know tuning forks are never made of plastic, so that's for good reason. Couplings and repairs. Sometimes even a repair can be a false positive, an indicator of a leak when we really don't have one. It's just a change of material. Different flow patterns. I've got tuberculation in a pipe. Maybe I've got some debris. Not all flows are the same, and so that traveling noise, that vibration through there is always going to be at risk for things like this. Ambient noise, street noise. We know that's a problem. Just a couple of minutes ago, I had to tell the guy with the leaf blower to be quiet outside my window here in Sacramento. Trenching, bedding can be a major factor in acoustic. Just as air bubbles and air pockets, as we're moving through, just that slight noise of that air pocket moving through can be a false positive that we've seen. And then, of course, the subjective nature of acoustics and AI, whether that's done by humans or even with some newer AIs that are out there. And of course, lower pressures. And what do I mean by that? It's how many times have we been asked by a vendor, look, what we'd like to do is we'd like to actually turn up the pressure. And studies all indicate, look, when you've got pressure in a pipe over 200 PSI, it makes it a lot easier to hear that sound. You start dropping that PSI into that 60, 70, 80 range, you can hardly see that leak. So what is Electroscan? Electroscan forgets all about that and simply measures the size of the hole. That's where the leak is. So is there some way that we can measure that without having any impact from all the things that we just talked about? We're going to go to our second quick poll. And it goes like this. Electroscan surveys are dependent on which of the following? Ambient and street noise, pipe pressure, groundwater surrounding ponding, flow velocities, and you can choose multiples here. All the things that impact us when we're listening. And we'll see the answers coming up here in just 1 second. Pipe pressures, yeah. And I've got none of the above. That's the correct answer. So that's the cool thing about this technology. Speaking of technology, my old partner in crime, Charles Wilmot. Charles, how you doing from outside of Dallas today? I hear you've got rainstorms.
A little, but I think we'll make it through.
Okay, great. I can't believe Charles is going to be visiting with us in just a few slides here. But Charles was actually doing Electroscan work when I was still running Hanson back in 2003, 2004. And so to see some of the awards that we've been piling up just in the last 2 years have been really amazing. And the big reason why Charles is even here with us is the number one question we usually get is how does Electroscan calculate, measure leaks in gallons per minute? There's a lot of high math. And so with Charles's PE and degree in aeronautical engineering, he's the perfect guy for that. The thing that we have to really construct here and understand is just the pure science behind this thing. And if you can understand or accept the science of this, I know that we don't accept a lot of science being discussed today for a number of things, but hopefully you'll understand this science. If I have on the same circuit two ends, and in water, I'm actually able to use water as the conductor to close the loop, to have electric current go from one end to the other. If you believe that science, then you believe the Electroscan concept of how we find a leak. And in fact, in using technology like COMSOL is a multi-physics, and we've tested these in labs and universities, this is precisely what the defect current looks like. And so as that probe moves through, it's interrogating 360 degrees of the wall of the pipe as it goes through, whether it's pulled through, whether it's a hydrochute or whatnot. So here's an interesting one, and just to kind of bring you in, Charles, what are we seeing here? Are we a technology that's actually pushing water through the hole? Is that how we measure the hole? What does this kind of picture mean to me, and kind of dumb it down?
Well, no, we're just passing an electrical signal from inside the pipe through the defect using the water as a conductor out into the wet soil where our ground stake picks it up. We're not impacting the flow in or out in any way.
So this could be zero pressure. This could be, zero to maximum flow velocity inside the pipe. This could be, we could have debris on it. Most debris is a non-conductive bed. There could even be some calcification that's on there. So those don't impact as long as you've got that connection. And I think this next slide, many people will talk about, well, how different is Electroscan with electromagnetic? And electromagnetic, some vendors do this, is not a leak detection tool. It doesn't estimate the leak quantity. We're doing basically a CAT scan of the wire framing, very popular in some of the PCC pipes that are out there. There is prone to interference that we have in there. Electroscan is simply electric current. And this is what allows us to locate leaks to 1 inch, less than a centimeter, to understand the severity, how much is that going through, and not prone to underground resources. And a very interesting thing that we're going to see is wall thickness. You see a little graph in there. We're going to talk about a couple of the case studies later. A full length wall thickness, not an average of the pipe. We want to specifically identify where that cement may not leak, but ready to go. And so, if we look at diagrams like this, Charles, so maybe you can help kind of explain what we're seeing as this light goes through.
Well, you see the two little black strips in the middle of the sonde represented by the two black dots. What that does is it focuses the leak detection signal in a narrow range, which gives us a sharper response image and helps us tie down the location better. And so that's where the term focused came from, and the term FEL, focused electrode leak locator.
Okay, great. So again, what we have is an electric current. It's just like that glass of water. And as electricity goes out of the probe, we have a grounding stake that is somewhere on the surface. It could be from 1 to 5 miles away. And once that gets and sees a finite opening, a fissure, a crack, a broken joint, a bad connection, then we actually kind of measure that electric current, is what you're saying. And really, as we look at those things, we know how to calculate an area of a triangle based on height divided by 2, area of a curve. The calculus that's really involved with things like this is really the calculating that area under the curve, that irregular shape, to look at that. And Chaz, how about explaining what goes into that calculus for computing a leak in pressurized pipe?
Well, as this slide shows, we started out with lab testing where we had defects of known size because we created them. We had a head that we controlled in an open tank. We used Torricelli's law to calculate the velocity coming out of that defect. And if you know the area and the velocity, Q equals VA, so you know the flow rate. We calibrated the coefficient of discharge in the calculations so that we could match the two up. Then we moved into the most significant, unique part is the geophysical equations, which allows us to relate that information to the Electroscan signal. And as you said, we're calculating the area under the curve based upon the amplitude and the width of the defect signal.
Okay, well, and I can understand part of that, but look, I think to be a little bit more focused on this, you know, the biggest difference that we're having out there is we do know that there's going to be a different flow rate, you know, based on pressures and pipe materials. So maybe kind of walk through this graph with the audience.
Well, of course, we have unitless discharge coefficients in the calculations, and we have different parameters that can vary. For example, the size of the defect versus the thickness, the length of the defect, which is the thickness through the wall in this case, varies from thinner pipes to thicker pipes, and we're able to calculate and to consider that in our overall calculations.
Mm-hmm. Okay. All right. So you know, just to kind of summarize this process, and again, we can have other technical sessions, and you know, this is part of the AWWA M77 manual that was published in 2019. So we're delighted to have that. But again, now in some of the revisions, you'll see us crossing all different pipe materials, including cast iron. You know, kind of what would you summarize, you know, in this slide?
Well, this shows the various steps that we've gone through in the past. We continue to laboratory testing, linking it up with the calculations and the calibration, using the geophysical things, and then field applications and verification, which is an ongoing process. We have some projects where we have flow data to compare to and other data to compare to. So that's ongoing, but we know that many parameters can vary when you get out in the field, out of the lab and out of a controlled situation. And we use a consistent approach and a uniform set of criteria for all the different defects in individual pipe segments and multiple segments and different jobs, so that we're able to compare them on the same basis. So we can say, you know, leak B appears to be twice as large as leak A, and leak C is half as large as leak A.
So if I can summarize that, you are saying that all leaks in a pipe segment, you know, and I could have point repairs in there, I can have change materials, but they are using the same calculation across all those points. So, you know, basically you're presenting a even you know, surface, a playing field to calculate those.
Yeah, a comparison based upon consistent criteria.
Yeah, good. So that's, I mean, look, nobody has done GPM. If it was easy, everyone would do that. So, you know, and I'm really understanding that. And you know, just to kind of run through what data looks like, here's a recent UK scan. You see, you know, 4 or 5 defects that are in here, but you can see on a relative basis that leak to the far left is very different from the leak to the far right. And I would almost tell you that's the leak to the far right that's the largest, because it's the area under the curve. It's how large that leak is, how much electric current is being measured through that. And the other benefit here is, which is just a major overcoming of the data logger scenario, where maybe 1 or 2 leaks are identified, finding those scenarios where every joint is impacted. And you know, I've seen it 100 times where, you know, new pipes that are being put in, these are some of the readings we're getting because the gaskets weren't putting in, they weren't safe. Angular rock is coming in. We're going to see some of the examples in here. So, you know, just the ability to begin identifying to this granularity, I think, is a major thing. And we want to be able to see, look, to know, yeah, we've only got 1 leak in there or 1 defect. and to see that. Here's just an example of the data that we'll do in some of the testing. You'll notice that plastic tube on the far right, hopefully it's not covered up, has 4 red circles. And you know, the probe is going up and down repetitively, and it's outputting all of the data to the left.
I couldn't hear what you said.
Sorry, that was mine. So Charles, explain what we're seeing in this scenario.
Well, this is a thing that we developed for different shows and presentations where the probe is moving up and down the segment of pipe, and you can see going down, you have defect 1, 2, 3, and 4. Coming back, you're measuring the same, 4, 3, 2, and 1, and they're essentially the same.
Well, this is kind of easy because, you know, you do the same. Of course, it's got to be the same. But, you know, what happens in other situations, we'll bring that up. You know, and then more importantly, what happens when there's not a leak? Because we see this a lot in CIPP. In fact, we're seeing this a lot in water lining projects that are out there. And IKT themselves did some live fire testing where we were looking at the leaks and the defects in CIPP. So scan 1 was upstream, scan 2 was coming back. So they were confirming that same thing. They're out of Gelsenkirchen, Germany. But the true test of this is over time. And I want to you know, talk a little bit about this RUL equation of remaining useful life. Because if we're finding this in a new CIPP, look at this, here's 2017. And let's say I come back a couple of days later, like 865 days later. This technology, number one, precisely locates the defects, finds they've gotten a bit worse, and it's actually picking up now new pinholes in this eroded lining. So I have all of the data in 40 years of Hansen mainframe programs that my dad and I did in the early 80s, in the 70s. I'm almost to the point where a pipe material and age and diameter has no bearing on useful life. It is almost down to what contractor put it in and when they put it in. To follow this kind of this finding permeability in the lining surface, let's see if we understand this. Again, if we can buy into that electric current, look at good CIPP. Notice there's no electric current able to get through. This is a watertight pipe at this particular location. On the right-hand side, that location is not watertight. Electric current is able to get through. And because electricity and water have a 1-to-1 correlation, I'm now looking at a technology that has the capability to measure the permeability of pipe materials, but not just on a piece-by-piece basis, but now on a 360 full-length basis. And why is that important? That is important because I now want to measure PCCP pipes, and I want to know what I'm most afraid of, which is that water main break that I can't see, that water main break I can't hear, and that water main break that electromagnetic may not even have the wires correlated to this. We all have seen stains of this. The purple is good, gray is bad. So the ability to actually look at cement lining without even having the steel reinforcement in here, we're measuring the permeability of that liner. And now can map geometrically from station point A to B. And so where I'm looking at the lowest point, those are going to be my most difficult areas. So looking at the secrets of our mining the data of our raw currents. Sometimes we can have 20, 30, 100,000 data points that we're now machine generating all this information. And if we do have a leak, there we go. Couple of other questions we get technology-wise. Is it safe? This is not the movie Boys in Brazil where we're asking if it's safe with Dustin Hoffman. You know, we all know that if we have electric lightning that hits water, that's a joule of power. But we don't have big fish kills from this, and this electricity fully dissipates in about 10 meters. Now, would I be swimming 11 meters from one of these? Probably not. But it brings to the point that this is a low voltage, high frequency electric current. So it's 688 batteries. It's 40 milliamps using 20 volt DC. And so all I have to do is have that water as the conductivity, a meter or 2 meters from the probe, because I've got to get that up, or otherwise it's going to dissipate. So there's no risk of it going up, following through to a household. Electricity can naturally dissipate. What does that mean with us getting to the grounding state? The minute it gets out the dirt, it can travel almost an infinite length. What about interference from underground lines? And again, we've had the luxury to kind of go anywhere on the planet. I happen to have a couple of buddies with Tokyo Metro, so we went over there with our translator and actually did one of the most difficult intersections. No dirt, nothing else. I mean, we had 3 subways going underneath this, no issues, no underground interference, clean readings throughout the Ginza. And that's one of the reasons why today this technology was actually awarded a water tightness testing standard by the Japanese institute there. You look at some of the other things that we did when Paul Boulos and some of the great guys that have been there now, Innovyze, now Autodesk. So integrating that data, that's why we have projects all over the world and kind of pick and choose the projects that we have. But enough about this. Charles, I want to thank you so much. But we want to see real data. You know, we don't believe this thing unless we do that. And we're now on to our last quick poll question. And the question is, what technology locates and measures leaks in liters per second? So do acoustic sensors, data loggers, low voltage conductivity, or FEL? This is what Charles calls focused electrode leak location. And the last one was data correlators, and satellites. So what measures automatically that GPM, again, across pipes? And I think there's probably, if you really talk to the real people behind this, there's probably a 10 to 20% give and take of the GPM. And we'll see the answer coming up here. There we go. Boy, everyone's getting credit for today's. So with that, we're going to get on to our last topic, and we're going to bring in our man of the hour, Brad Weston from London. You know, Brad, great to have you. Delighted to see you there at 6:30 in the evening. So good evening to that. And I think the first thing I want to do is say congratulations on the big win. Your recently signed a framework contract with Yorkshire Water. That's just an amazing feat. So happy that that happened, and I just wanted to say welcome.
No, that's brilliant. Thank you very much, Chuck. Again, with Yorkshire, it was definitely a team effort, and I was glad to take the lead on responding to Yorkshire's Lot 5 Clean Water Innovation Marketplace. Okay,
so look, I see this as an 8-year, so I think all my girls will be out of college by the time this ends, so that's great. Worth 500 million pounds. So why did Yorkshire Water call this Lot 5? What's that all about?
Okay, so lots 1 to 4 included emergency and planned reactive work. It included developer services for cleaning lines and new mains. It included metering work for replacing, installation, repair, and meter reading. So basically, altogether, they totaled £800 million. And then Lot 5, where we come in, is also known as the Innovation Marketplace. Basically, that's designed to generate competition among successful bidders. and it makes it easier to introduce new technologies to the water utility sector.
Wow. I mean, this is, this is truly a landmark tender. I know you've done projects up with Yorkshire already, just some wonderful people. Got some great consultants that are out there, some wonderful solutions as well.
Yeah, and I think you and I both, saw this right away when Yorkshire Water published their first draft of their innovation roadmap back in September 2020, and then again when they updated it in 2021, like it's shown here on this slide.
Yeah, I mean, when we saw this a year ago, we saw leakage. That was a integral part of this. And I was really surprised to see them include capital efficiency, this CapEx, technology. So that was very cool. And then the other thing is, I was really excited because of our response. We actually included, all three of the products that we have: Delta, which is Electroscan, CCTV, and Acoustic; Trident, which is a push reel, that's Electroscan and CCTV; and our secret weapon, Swordfish.
Yeah, me too, Chuck. We've actually done a lot of field testing on all three of these projects, and at the moment we're getting good responses from our benchmark projects as well as our Amazon Web Services, which is a critical H2O cloud performance.
So what I particularly liked about these challenge statements was it covering this QA/QC of trenchless technology. So we started the first trenchless projects in England. They came out of England in I think 1971. I was still high school. I'm class of '74, so I was still in school when it first came out. But today it's a fairly complex, and you're seeing 4 different water CIPP projects, all from the UK, I might add, because we're doing a lot of that. But now that we have 4 different types of curing methods, and we have alternatives like spray in place and spiral wrapping. So what did you think of this when you saw the detail, and that they accepted kind of our solutions to help with this test?
Yeah, I totally agree. Water utilities never really test their liners for water tightness, since CCTV cameras usually do that, and tap connections often prevent hydrostatic testing. But what utilities really want to know is that liners remain watertight after installation and after being pressurized as well.
Yeah, what I'm seeing is that when the directly after curing, the pipe hasn't been rewatered, hasn't been pressurized, and some of the liners can just look off, like the liner here to the upper left. And you really, and I know, not to give it away, some of you may already be looking at some of the slides that you've downloaded in the PDF. We're going to see some other liners here, but you really have to look at that pipe and its dynamics after it's been fully pressurized, and you do have flow. So, well, enough about that. How about narrating kind of what you do out in the field, Brad? Are you ready for that?
Yeah, happy to. So as you can see, this is our service center located in Swindon. So here we maintain and prep both our sewer and clean water kit for projects in separate designated maintenance areas. The data system you can see here was being prepped for a project whilst crucial project planning was taking place, such as maps, GIS planning, and aerial view reconnaissance. So working with various contractors, and as you can see here, our team is setting up on one of the pipes, and the line's pressure is being constantly monitored for any change or deterioration. So this clip here is us setting up a delta survey in the middle of the countryside. All equipment is kept off the ground to prevent contamination to the water supply, and has been sterilized using a chlorus solution. You can see there, that's my senior technician, Chris Chesworth, pointing out the bolt pattern to make sure that the plate is done up and securely. You can see this is because we want the flange to spread and seal evenly. So once this has been achieved, we attach our launcher and set up our electronic equipment to carry out pre-tests before the probe enters the line. You can actually see here when I walk over, the launcher has now been pressurized with the line, and we are now good to go and scan. So the reel feeds into the launcher and into the line with myself and Chris Chesworth assisting the cable into the launcher. So this is what's happening inside the pipe. Once the probe has been inserted, the flow will inflate the hydrochute and carry the multi-sensor probe down the line. As the probe goes down the line, FEL, acoustic and CCTV surveys are being carried out at the same time. Our FEL is monitored constantly through our mainline application software to look for points of interest along the line or a very visible defect, for example, a leak in a pipe. So when we get this information, from our data that's being collected through our grounding source that you can see being placed onto the ground, just here. And while that's happening, we are collecting acoustic points of interest, which is being marked down by the operator on the side of the van. So the survey will continue until we've reached the required distance given by the client, or if we're looking for a certain objective. And then it is retracted back out of the pipe by our ground crew. And in this case, it was myself and Chris Chesworth. Obviously, you can see that we wear all the relevant PPE to make sure that we keep the cable clean. So here's a quick glimpse of the raw defect current graph that's generated at the end of the scan and is also recognized by AWWA's M77. So Electroscan's leak detection equipment is a precision-based leak detection tool with a locational accuracy down to just 1 centimeter. And that's all for that video. So back to you, Joe.
Yeah, great. Okay, well, let's slow down just a bit, and let's Brad, that was very informative. I appreciate that. That's a kind of a typical thing. So how about we dive into some of the metrics, some of the real numbers that we get. This is one of your Delta projects in the UK that was about 171 meters, 24-inch cement mortar line ductile line. Tell us about that.
Absolutely. So this was a water main that was trying to be newly commissioned, but it actually failed multiple pressure tests beforehand. So we typically would have used our Hydrochute to propel our probe through the pipe for this project, but because the flows were minimal, we decided to do a pull-through setup instead. So this is a chart you can see here we used to match the size of our Hydrochute to the flow and diameter and pipe that we are entering that day. So we arrived on the job site, we got everything set up, and we actually completed all the work in just under 3 hours.
Wow. So Brad, did that include finalizing the data? I mean, I see you got a spike up there. What kind of reporting did you have available on site?
Yeah, so that did include finalizing the data. So what we actually done is we partnered with an internet provider named T4S that gives us 98% coverage of the UK market, which is obviously really needed sometimes. And within 5 minutes, we actually had all our results with us on the site that we could present to the client.
Yeah. Yeah, I really love, I know there's Microsoft Azure out there. We've been at Amazon Web Services, a partner for almost 10 years. They've got 9 of their satellites around the world. So globally we have this. So whether we're in the Strait of Hormuz, north of Dubai, or in England or Australia, we get the same kind of uptick worldwide in this. So it's a real impressive thing. So look, I know that we were kind of the vendor of last resort. The contractor was pulling out his hair. I know that previous multiple acoustic testing, including a tethered acoustic probe, didn't find any leaks. So how did our acoustic do?
As a matter of fact, we didn't actually find any acoustic anomalies either. All the anomalies we actually heard was the probe hitting against the wall of the pipe, which in my experience happens most of the time when someone uses a technology like an untethered acoustic ball.
Well, and look, I know you're listening I mean, it's a hands-free operation. So you're actually listening, and you showed a picture of that, listening to the acoustic. You've done 3,000 insertions. So you've heard a few acoustic leaks in your time with some of the other products when you work for WRC. So, so I understand that. Let's do a flip on the data side. So this is the kind of data we translated it from liters per second to gallons per minute. So this is kind of a subset of the data that is available. I like to say under 10 minutes, mostly it's 5 minutes, so that we can actually see the position of this. And this is really key. We want to see just how many leaks, what the severity of those are. So if we do have the camera that's still in there, and again, some of the summary data of that area under the curve, we want that instantaneously known. In this particular case, what we're able to do is, because where we saw those two big leaks, we're able to go to the biggest one and now see matching an angular rock that was put in there. This was a new pipe that was installed. And so now we can definitively say, look, that is not just a rock in the joint. That is a leak. Water is, electric current is passing out of there, and that's why you're losing pressure. So it's a great indicator of that. The other thing that I want to say is we're now evolving. There's a lot of AI in this, and I'm not a big fan of AI for acoustic. If we're missing so much for acoustic, that's a lot of brain power, for what we're actually not hearing. In our case, we're really looking for ways that we can identify and match the leaks that Electroscan is finding to fixtures in that pipe. Is it at a connection? Is it at a joint? Is it in the wall of the pipe? And so since the TV camera has the same footage encoder as the Electroscan probe, we can match those up, and now we can with 99.9% accuracy identify that to features inside of the pipe. We'll switch gears and do a US study, and we have our Trident. I'll let again, we borrowed from this from the UK, but and Brad will talk about this in a couple of minutes. But here in the States, we typically enter through hydrants. A lot of other great companies have done this before. It's just they used acoustic, and so it was TV and acoustic. This is TV and Electroscan. So as we look at the flanges that are built on our Trident insertion tubes, whether we fit directly over that, we look what the bolt patterns are. We're able to put our camera directly into that, closing that. We see how our chlorination chamber will chlorinate that cable as it goes through the pipe by pushing the pipe through. This is usually a 2-person operation. I'll get and show you a picture of that in a second. But again, cameras are great for positional navigation. Is this valve open or closed? We want to make sure that that's open. Do we have extreme calcification in that pipe? If it is, we may want to back out, have that pipe cleaned before we do that. And then getting that good TV, we know that TV can't find the leak. They typically go outside of the pipe. And so really having that scan, whether we're pushing or pulling back, is really what the Triton is all about. This is a 400-foot push reel, 120 meters for our British folks, and that's the ability that goes in. So here's an example. Here we know there's a leak. We see the water, and it's about 10 gallons. So the problem is, where's it coming from? Is it coming from the track where we can't really get to, or some other location? And so the Triton was perfect for this. We had an entry point that we could go into. Typically, we'll either enter through a hydrant or hot tap or valve that goes in. We like to put a flow meter into that entry point, so we measure velocity. We know what the velocity of the flow is. We know the direction of the flow, if there's any question about that. We've got a chlorination area, so any of the instrumentation is cleaned before it's installed. It's very carefully put in place. Everything is done under pressure, so we'll confirm where that pressure is. And notice I said it's a two-person crew, only because the footage encoder is actually on the reel itself. So what we want to do is we want to position that camera at 0. Our accuracy we claim is 1 centimeter. In a lab, it's 1 millimeter. But really what we want to do is when we enter the pipe, that is where 0 begins, because we want to be able to know where that is inside of the pipe. And so as we're taking a cable off of the reel, we want to be putting that in the same so we have a nice, easy flow for that. We look at the data, we're capturing the video, but this is a big difference now. And I'm going to talk about AI from a pretty different thing. Here I find a leak. Now what I want to do after I get the probe out, or maybe when the probe is still in, I may want to do something else. If I find out where that leak is, I may very well, and if in this case, in the center of the rail track, so, and this is only a 4-year leak that goes back, that's already leaked 20 gallons of a 24-inch lined steel pipe. But I want to do something different. I may want to position and stationary point my camera and look at the flow and see, as in this case, if I can see bubbles actually moving towards the leak itself. You can only do this if you have accuracy in leak detection like Electroscan. So if I tell you where the leak is and tell you where to look, instead of having a continuous CCTV, then I can stop and reposition this. That also brings a whole new level of AI where you can measure the flow intricacies. This is where we're now going to with TV. And I need in some cases a higher resolution to do that. Fortunately, I don't have to reinvent the wheel. Q's was kind enough to do the FlexiProbe C540. So if that looked familiar, we just add a few attachments when we sell it to utilities and contractors, and also include insertion tubes to do that. Third case study I'm going to go through real quickly. Here we're coming in a 12 o'clock position. And then not only that, but also a 3 o'clock position. As we see, these trenches have to be 8 to 12 feet. You can see where our truck is relative to that. And now you can see where we come in and start measuring wall thickness and decay. So not just finding the leaks. This is not what electromagnetic does. This is what electric current can do, low voltage current. Brad, I'm going to jump back across the pond. Tell us about this little case study before we wrap up this section.
Yeah, so firstly, I'd like to thank Thames Water and PN Daily. So without their request for us to make a small diameter push rod system for clean water in PVC pipe, the Trident wouldn't have actually been made. Trident was purely created down to a client asking us, could you make something that could do this? So back to the case study, the pipe was in an old part of London, approximately 140 years old. But unknown to everyone, the pipe was actually a cast iron pipe. It was supposed to be PVC. Even though the pipe was cast iron, we still actually managed to find 9 leaks on that line that was identified to the client straight away.
Yeah. It was, I was seeing the upload and seeing, I thought you had a typo when you put in cast iron for this one. And the last case study, do you mind sharing what happened on this recent project for an unnamed UK water company?
Yeah, absolutely. So this one was a real mystery for the water utility, as they had experienced a series of main bursts and didn't quite know what was happening with the flow. So we first tried our Hydrochute on the Dove system, but when the flow is measured 0, we decided to use our Trident push reel, which obviously has CCTV and Electroscan only. And we were a bit surprised with what we saw in the leaks that we found. So we saw a pipe that had multiple recent point repairs, where most of the new joints were either installed in an offset position or quickly settled. Not only did we see joint separations, but we saw dirt above the pipe. The water company was there and actually immediately reported the results up the ladder to arrange any necessary rehab. The reason this was a vital line was because we were located across from one of the major hospitals in the area.
Yeah, non-trivial. Well, thanks on that. Kind of eye-opening. So, you know, we're coming to the end of this section and before questions, but we're now seeing, at least in Electroscan clients, a demarcation line being drawn, and that is what is defined as smart leak detection is really more water tightness testing. You'll never see it in any of the inspections, but what we're now seeing is if a pipe looks like this before, we want to do a before and after test where we've got maybe one or two things that we can quickly fix, hold a contractor accountable for that. We all know kind of the intricacies for hydrostatic testing. I've only been around hydrostatic testing for 40 years. I think my 13-year-old daughter could fake out a hydrostatic test at some of the pressures we have in some of these things. What we don't want to do is we don't want to have a situation where we have leaks before rehab, and then we're actually having more leaks after rehab because of some of the damage that can be done. And that damage can be in reopening some of the taps as we look at those lines coming in. So, and this is what we're seeing. And so I would almost have to say that, you know, as I look at leak detection, you know, for our company at least, I mean, the number one thing we're focused on is we want to present, no kidding, unambiguous data on what pipes are good. And I think we can do that with this technology. So CapEx avoidance. And in the UK, we're busy over there because they've almost had to recapitalize all of their pipes and put them on a replacement. Some pipes don't need to be replaced. The targeted surveys that we're doing for leak, reduction in non-revenue water, some or all of you can benefit from that. The QA/QC of pipe repairs when that pipe is back under pressure. And then as we see in some countries, just looking at illegal connections and knowing which ones leak and don't leak. So as we look at the water balance and unpack that, I think the products are pretty relevant. It's one more tool in the toolbox, depending on what you do. I do want to say in closing that December 7th through the 9th, we've got 3 very interesting water papers coming up. Another AWWA sponsored event at the North American Water Loss 2021 in Austin, Texas. Yeehaw. So we're looking forward to do that. And with that, I am going to open up questions. And I can already see I have another series of things that's coming through here. And if we can't get to all of them, we've only got a couple of minutes left in here, so we'll just do a couple. Apologize for that. Keep your questions coming in. We will account for those and then distribute all those to everyone. But one of them came up, Brad. A question I'll pitch back to you as our first question. The question is, are the products that you're using in the UK the same ones that are being used in the US?
Yeah, so exactly the same. The only difference is in the UK, we measure in meters, and in America, obviously, you're measuring in feet and inches.
And you drive on the wrong side of the road, too, I think.
Debatable.
What about the insertion tubes? So, you know, you obviously, if the probes are the same, you have different size pipe. How are you handling? How are the two countries handling that?
So with the UK launcher, system launcher, and the design of the flanges, it's designed to the UK and EU standards, whereas the Americans launcher and the flanges are obviously designed to the US standards. So that's the difference.
Okay. Great. So, and then can we get you over here to the US to do projects?
Absolutely.
Are you tested? Because I think they're opening up, you know, the airlines to go back and forth more freely over here, Brad. So, Brad, I thank you. I know you're coming up to 7 o'clock, and I'm taking you away from the pub but I know you just started a 50-kilometer project down there in Southern Waters. So thanks for spending the time with us. Another question that's coming up, I'm not sure if this is from an acoustic vendor or not, but it's saying, how does Electroscan measure and benchmark acoustic versus Electroscan? And why do you keep saying that that acoustic is missing 80 to 100% of leaks? So to be honest with you, that number that we're comparing is probably closer to 95%. But I think there's three reasons for that. There's a lot of wonderful acoustic listening devices, and I would almost have to say of the sensors, data loggers, probably the number one thing that even our guys use are listening sticks that are out there. And I've had one for over 30 years. But you've got to realize that our Delta does include a third-party acoustic sensor. So in every one of them, we are picking up acoustic from a tethered, industry-accepted. They don't do conductivity, but we do it. And we kind of did that just so that we have a benchmark. We want to confirm what that information is. I think the second thing is, it's very interesting. We've been doing projects in water for almost 5 years, but today is our first US webinar. So I appreciate all of you staying with us this long as we come up to the top of the hour. But in the past, what we've done is we've been called in as the solution of last resort. Hey, we've tried everything. We've tried our listening sticks. We've tried correlators. We've tried helium tracers. We've done pressure transients. We still can't find the leaks. And so we'll come in and do it. So, I guess the number could be higher than 100, for the 5 times. And in a matter of a couple of hours, we can do that. The third thing that I think we really need to be open as an industry is and because we've been hearing and sniffing, smelling based for such a long time from a sensory standpoint, is I think we really need to be open and honest about some of the drawbacks of acoustic. And whether it's Mother Earth, whether it's climate change, whether it's just the ambient noise, the industrialization that we're going through, having to do most leaks, acoustic has been with us for such a great time, but it is a real challenge. We're up against that, and so we've just decided to go a different way of measuring the size of the hole to do that. So hopefully that answers that question. I've got one more question. Charles, are you still there outside of Dallas?
Yes, I am.
Okay, so there's always one, and this question is having to do with soil resistivity. How does the soil change the Electroscan's readings? Charles, you have 1 minute.
Okay. Well, the soil is moist under the surface, and we've done almost 3 million feet since 2004. We haven't had hardly any cases where we did not have a strong enough signal to pick up with our sensitive equipment. And so we also have a rheostat on the rig, which we can adjust the strength of the signal. So we need to get the signal back so that our equipment can pick it up. And yes, there are many variables and variances, but that has not been anything that has hampered us or significantly impacted our data in a way that we couldn't deal with.
Yeah, what I really liked is that before I've seen any scan on the planet, we will recalibrate the equipment not only for the atmospheric change, but also for the soil, so that we maintain that correct range of electric current. And the secret behind having similar leak sizes and locations and severities, not just during the same scan, but next day, 30 days, 60 days, 1,000 days out, is because we do that. So whether it's a different crew, it's different equipment, it's different locations. And look, I've been in outside of Abu Dhabi and Dubai the dead of summer, when the soil has been so dry. I know the tricks to actually maintaining that conductivity. We've had to pour some water to weten the grounding stake. But once we get that current, we're good. We know that there's going to be a closing of the gap if there is an opening in the pipe. And with that, we've come up to our 11 o'clock hour. On behalf of Charles Wilmot outside of Dallas and Brad Weston outside of London in Swindon, I'm Chuck Hansen. I thank all of the folks from AWWA. If you would like to request a copy of this identical PowerPoint stack, email me at chuck@electroscan.com. And we're happy to send that to you by the end of the day. So with that, I thank you and have a great rest of the day.